Hello everyone and welcome to another section 7.3. This section is on geometric sequences and series. In section 7.2 we looked at arithmetic sequences and series. Two are the attributes of the sequence and series, one of each, that we are interested in are as follows. One thing is the formula for the nth term, and the other is the formula for the nth partial sum. Okay, so we're going to do the same thing. We're going to follow the same theme as we did in section 7.2, arithmetic sequences and series. Except now we're going to talk about a very important class of sequences and series, geometric sequences and series. The series are used quite often in calculus courses, and they have wide applications. Very useful series, so and very important in our work. So let's continue and let's check this out. I'm gonna black this thing out. Don't worry about incents. There are no units on this. Just black it out. Okay. So what is a geometric series, or I'm sorry, not series, sequence? A sequence or a geometric progression. So in the case of a geometric sequence, again, what we have is the following. You start with the first term. Just like before, you have these consecutive terms of a sequence, right? Dot, dot, dot. An infinite case. And what's special about the geometric sequence and makes it geometric is that if you take the ratio of two consecutive terms, it's going to be the same. So that means if I do A2 over A1, if I do A3 over A2, and it has to be in that order, by the way, not the other way around. So it's not A1 divided by A2, A4 by A3, and so on. All of these will give you the same ratio. Ratio because we're dividing, so we're going to call that a ratio, right? Remember, ratio is equality of two fractions. Or actually the ratio, I mean the technical jargon for it, it's okay. It's just like a fraction. We call it a ratio. All right. Now, the more general form is what you see here. So in general, you take the next term divided by the term previous to that, and you get what we call the common ratio R. So in this example, for instance, if you look at the ratio of 2 to 1, it's the same as 4 to 2, same as 8 to 4. See the next one over the one before. These are all 2's. So we do have a common ratio in this sequence, right? We have a common ratio. Now, one way we can also do this is, let's say I have the sequence 1, 2, 4, 8, and I want to create these other terms. So once we figure out the common ratio, call it R, by dividing, say, second by first term, 2, you can actually multiply the term times 2 to get the next term. So 8 by 2, 16. Multiply it by 2, you get 32, then 64, and so on and so forth. See how that works? So we can use the common ratio to generate the sequence that way as well. But this formula is going to be important for us, that for the common ratio. Now, how do we come up with a function, the nth term of a geometric sequence? You're looking at it here. And the one next to it, of course, gives you the formula for the nth partial sum. That's what this one is called. This is the formula for the nth partial sum. And again, it's called partial because it's portion of an infinite geometric sequence. So if I look at the first 50 terms and I want to add them up, then I have a geometric series, and S sub 50 is what I want to do. So that 50 is only portion of an infinite set. That's why I call it the partial sum. So let's take a look at some examples here and how we're going to use this one. So for instance, let's say I'm making an example up here. Suppose in this example, The sequence is 10, negative 5, 5 halves, and negative 5 fourths. Okay, suppose that's my sequence. And I want to find the fifth term, a sub 5, and I want to find the general term. How about the function itself? So using general term, I can just plug it into that formula, this one, once we tailor it for my example, put the specifics in, then I can find the value of any term, right? I can do the 50th term, the 100th term, the 1000th term, and so on. So first, we need to find a common ratio. For common ratio, divide the second term by first term. So I get negative 1/2. You can divide any two back-to-back terms. It's easier to divide the integers. So there's your common ratio. So what is the fifth term going to be? The fifth term is when you multiply the fourth term by common ratio, right? The term before times common ratio. The fourth term is negative 5 fourths. Multiply by negative 1/2, and this will give me a positive 5/8. So that's going to be the value of the fifth term. Notice, by the way, the common ratio here is negative, right? And one thing that common ratio will do to a geometric sequence is that it will cause the sequence to alternate. Look at this. You have positive, negative, positive, negative, positive, negative terms, which we call alternating sequence in this case. All right. So what is the nth term? Well, the nth term of this example is first term times common ratio to n minus 1. The first term is 10 times the common ratio is negative 1/2 to the n minus 1 exponent. So there you go. That's the function. If you want to know what the 8th term, 7th, 70th, whatever, you just plug in that number in here. So for instance, let's say I want to know what the 7th term is. A sub 7. I do 10 times negative 1/2 to 7 minus 1. Plus 10 times negative 1/2 to the 6th power. Now negative 1/2 to the 6th power, that's going to be, let's see, 2 by 2 by 2, 6 times, right? That's 2 to the 6th, 64. So it's going to be 10 times 1 over 64. And because I'm raising to an even exponent, the negative becomes positive. And there you go. So the 7th term is 10/64. And of course, we can reduce it, right? We can simplify, we always do in math. Divide the 2's out and we get 5/32. That's the value of the 7th term. So that's why the formula is called the general term. It can give you any term in the sequence. Now, the formula itself, I left it unsimplified here. We could actually work this further, okay? To me, this is good, but here's how we can go further with this. So here's my 10. The negative 1/2 to the n, or n minus 1. Write it as negative 1/2 to the n times negative 1/2 to negative 1, right? Remember the product rule of exponents. A to the m times a to the n is a to the m plus n, right? So here I have the sum, just like I have here. So I'm combining two numbers. I can write those separately as product in the form of multiplying exponents. So there you have it. Think of this as a to the m and this one as a to the n in here. So what does that mean? What is it going to do for me? Well, negative 1/2 to the n, I'm going to keep it. Now, negative of 1/2 to negative 1. Let's take a look at that one. To negative 1. We can use the negative exponent rules to do this one. I just flip the fraction inside parentheses and change that to a positive exponent. There you go. So this is going to be negative 2 over 1 is negative 2 to the first power is negative 2. There. That's what that is. Okay. Therefore, I'm going to multiply it by negative 2, this number. And a negative 2 times 10 is negative 20 in front. That's this product. Negative 20 times negative 1/2 to the n. See how I'm just really torturing this thing step by step. Now, the negative 1/2 to the n, by the way, I can write negative 1/2 to the n as negative 1 to the n times a half to the n. True? We can do that. We can split this into a product. And, of course, the negative here, I can work it in with this negative. Check this out. Negative 20, negative 1 times 20, negative 1 to the n, half to the n. Again, the book probably won't do this, but I'm just having fun with this. Negative 1 to the first, negative 1 to the n. So this is going to be negative 1 to the n plus 1 times 20 times half to the n. So it is possible, my point is, it is possible to manipulate these nth terms, especially for geometric, to get to where we get this totally different expression. But again, in your book, I'm pretty sure they probably leave it in this form. And that would be good enough. This form reinforces the general form. First term, a1 times r to the n minus 1. So, again, I'm happy with the form that you see right now that I'm circling, and I just circled, and I erased it. So I'm perfectly good with this, but it is possible to, again, manipulate these to however we want to. All right, so we're done with this example. Let's take a look at another example now. Let's say I want to add a few terms of a geometric series now. So suppose my geometric sequence is 18, negative 9, 9 halves, negative 9 fourths, and so on. Okay. And suppose I want to find, let's say I want to find the sum of the first 5 terms. Okay, just some random thing. Find the sum of the first 5 terms. In other words, I want to find the sum of the series that has 5 terms. Now, my common ratio is, remember, second term divided by first term. So it's going to be negative 1/2. That's my common ratio. The sum of the first 5 terms, this is what it is, S sub 5. That means 18 plus negative 9. I'm looking at the sequence. Negative 9 plus 9 halves plus negative 9 fourths plus one more term. Notice, by the way, as I go from one to the next, to the next, to the next, each time you multiply by negative 1/2. 18 times a half is 9. Negative makes it negative 9. 9 times 1/2, 9 halves, but it's negative, so it's going to make that positive. 9 halves times 1/2 is 9 fourths. The sequence and the series will be alternating in this case because r is negative. So to go from negative 9 fourths to the next term, I multiply by 1/2. And because this term is negative, the next one will be positive, the 5th one. And it's going to be 9, 4 times 2, that's half of 9 fourths. There you go. We want to know what is this sum. So if you like, use it on your calculator, do it, see what this is. However, that's going to miss the point of this example. So what we want to do is we want to use the formula the formula for the nth partial sum, and that is this one. S sub n is a1 times 1 minus r to the n over 1 minus r. Of course, division by 0 is undefined, so this will not work if r is 1. The common ratio is 1. That will not work. But then again, if the common ratio is 1, the sequence is not going to be geometric anyways. You're just going to get, for example, if I start with 100, common ratio 1, next one is 100, 100, 100, 100. That's not a geometric sequence. Okay, S sub n, a1, 1 minus r to the n over 1 minus r. So let's write that formula for reference. It's going to be a1 times 1 minus r to the n over 1 minus r. Let's put the specifics in. The sum of the first 5 terms will be first term remember is 18. 18 times 1 minus the common ratio is negative 1/2. And n here is 5, right? N is 5. And divided by 1 minus the common ratio. Notice the common ratio is negative and you have to keep it in parentheses so we can distribute the signs appropriately. So this is going to be 18 times. The numerator of this fraction is going to be 1 minus negative 1/2 to the 5th. That means 1/2 times 1/2 times 1/2 and so on, right? 5 times. So 1/2 to the 5th is going to be 1 over 32nd. The negative of 1/2 to the 5th will be negative 1/32. And then there is a negative in front of parentheses, right? So that's 1 minus negative 1/32 divided by, in the denominator, double negative on 1/2 makes it positive. That's 1 plus 1/2. And the numerator, double negative makes positive. So that's going to be 1 plus 1/32 over 1 plus 1/2. True? Now, let's see how we're going to do this. 1 plus 1/32. One thing I could do, because again, I seldom use a calculator. Let me write down first of all what I have here. So that's 1 plus 1/32 over 1 plus 1/2. Okay, now this fraction is what we call a complex fraction. A complex fraction is a fraction whose numerator or denominator or both themselves have fractions. So typically what we do in a complex fraction, to get rid of making it a simple fraction, we multiply top bottom by LCD. In this case, LCD of 2, LCD of 32. So I'm going to do that. That would be 32. So we multiply top bottom by 32. That's going to be 32 plus 1. I'm distributing now. 32 times 1 is 32. 30 times 1 times 1/32 is 1. In the denominator, 32 times 1 is 32. And 32 times 1/2 is 16. So this is going to be 33 over 48. True? That's what that is. Okay. 33/48. Now, let's see. This fraction is divisible by, what you call it. Let me write it first before I lose this. It's 18 times 33 over 48. Now we can actually reduce the fraction, divide the top and the bottom by 3, so it's 11. And 48 divided by 3 is going to be what, 16? Right? Yep, 11/16. So we've got that one down. Therefore, the sum of the first 5 terms is going to be 18 times 11 over 16th. Now 18 and 16 are even, so that means they have 2 in common. That's going to be 9 times 11 over 8. So the answer is going to be 99/8. there you have it. So again, you're welcome to add them on your calculator this way. And if you do, now I can remove the question mark. I'm going to replace it by 99 eighths. And please verify and see if this is right. Hopefully it is. If it's wrong, I don't want to know. No, seriously, if this is wrong, please let me know. Either email me or leave a comment, and I will adjust and fix this, do a correction to the video. Hopefully it's not. And there you go. That's the sum of the first 5 terms of this sequence. Okay. Now, let's try another example. Let's try this one. How about, and this time I want to do something that's in sigma notation. So let's say I want to do sigma k4 to 10 of 2 to the k. Notice, by the way, the lower limit of the summation is not a 1 and it's a 4. So if I write this thing out, it's going to be 2 to the 4th. Start with the lower limit and count your way up to the upper limit. 2 to the 6th, all the way up to 2 to the 10th. This is going to be a huge number, isn't it? Because 2 to the 10th, that's a large number. All right. Now, this series is going to be a geometric series. And you can see, I can go from 2 to the 4th to 2 to the 5th by multiplying by 2. Next one, multiply by 2, by 2, by 2, by 2. So it looks to me that the common ratio for this geometric series, the common ratio is 2. And the first term is 2 to the 4th, which is 2 by 2 by 2 by 2, 16. This will identify the geometric series uniquely. First term, common ratio. And so let's see, what are we doing? From 4 to 10, how many terms in the series am I adding? Right? 4, 5, 6, 7, 8, 9, 10. These are the terms. How many terms? 1, 2, 3, 4, 5, 6, 7. True? There are 7 terms, beginning with 2 to the 4th, ending with 2 to the 10th. True? Now, so we have 7 terms. Keep that in mind. And therefore, n is 7. And what I really want to do is, for this geometric series with these characteristics, with these specification, I want to find the sum of the first 7 terms. S sub 7 again. It's going to be, let me write the formula one more time. It's A1, 1 minus r to the n over 1 minus r. True? Now, let me hide this one. We don't want this yet. We're getting there in a moment. So let me plug it in. So S sub 7 is going to be first term. First term is 16. 1 minus common ratio is 2 to the 7th divided by 1 minus 2. So this is going to be 16 times. 2 to the 7th now. Let's see, what is 2 to the 7th? 8 by 8 by 2. That's 64 times 2, 128, right? That's going to be 2 to the 7th power. 1 minus 128 over negative 1. 1 minus 128 is negative 127 divided by negative 1 is just 127. Right? So for this one, I just need to multiply 16 times 127. Okay? And for that, honestly, I'm going to use a calculator. That's going to be 2032. That's going to be the sum. Wasn't as large as I thought it would be, but it's still reasonably large. But there is the sum of the first 7 terms. And again, you are welcome to add those individually and see for yourself that indeed that would be the sum. Okay, so that's how we worked that one out. And now we've done enough of the formula for the nth partial sum. Let's actually look at the last idea of this section. And the last idea is this. I'm going to actually move this away and explain something. Going back to S sub n, a1, 1 minus r to the n over 1 minus r. Now, if the common ratio in a geometric sequence, if the common ratio, let's say absolute value of common ratio is less than 1, because remember, common ratio could be negative. We've seen an example of that. But if the absolute value of common ratio means ignore the sign, the number itself without the sign is less than 1. So for example, let's go 1/10. That's less than 1. And let's take a look at powers of 110. So for instance, 110 to the 4th power. That's 1 over 10,000, isn't it? In decimal, it's a very small number. And what if I go 1 over 10 to the 8th power? Isn't that 1 over? I have 8 zeros now, correct? That's 6, 7, 8. So that's going to be 1 over 100 million. 10, 100,000, 10,000, 100,000, million, 10 million, 100 million. Look at how small that number is. Imagine if I write this as 1 over 10 to the 20th power now. That's going to be a very small number, isn't it? It's going to be indeed in decimal. You're going to have, what, 19 zeros? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Might as well go 9 more. 1, 2, 3, 4, 5, 6, 7, 8, 9. How about that? Ooh, look at that number. For all practical purposes, we're going to say, that's almost 0, isn't it? Close enough. So, the takeaway from this, if the absolute value of common ratio is 1, you can see how the part that is r to the n is eventually going to approach 0, isn't it? Okay, so it's going to get smaller and smaller. So, if absolute value of r is less than 1, I can write the following. I can say that if that's, then r to the n is going to, I'm going to put an arrow, means it approaches towards 0. The arrow, read that as approaches. It gets very, very, as you can see, very close to 0, right? For large n. And as you can see, n shouldn't be really that large. I mean, 20, that's not very large. Imagine if I have 1/10 to 1 millionth power. Isn't that very close to 0? So, the statement makes sense. r to the n approaches 0. Okay, and if r to the n approaches 0, what is this going to happen? Well, r to the n is going to go to 0, correct? So what can we do? We can write s sub n as a1 times 1 over 1 minus r. True? See, I made this part 0 because it's going to get very close to 0. And I can now remove parentheses and multiply a sub 1 times the numerator, and we get something very cool. The sum of nth partial sum is going to be that, and here's what I'm going to change. Because we said n gets very large, right? R to the n approaches 0. How large is large? Well, we're going to go for the top. We're going to call it infinity. How large? Infinite. So, this definitely r to the n is going to approach 0, and what we are looking at here, it's called the sum to infinity. So, this is very fascinating, folks. This is very interesting. It is possible for a geometric series to sum means to add terms to infinity, and actually get a number that is very darn close to the total sum. Isn't that cool? So this is what this little nugget tells us. Some of the terms of an infinite geometric sequence. So here's how it reads. The sum to infinity, notice the subscript infinity, of terms of infinite geometric sequence, first term a sub 1, common ratio r. It's very important that absolute value of r to be less than 1. If it's not, we say the sum diverges. It just blows up. We cannot do what we're about to do. So it's got to be less than 1. But with these specifications, then it is possible to write the sum to infinity as a sub 1 over 1 minus r. Okay. And right in here is the statement I just made, commented about. If absolute value is greater than 1, this thing's going to blow up. It's going to blow up. That means it's going to diverge to infinity. It's going to grow without a bound. Okay. So in that case, there is no, we say, limit. As n goes to infinity, remember, n approaches infinity. And that's how we're going to write it. Okay. So let's take a look at an example of this one. Just probably one example suffices. Suppose my geometric series is negative 48, negative 24, and negative 12, and negative 6, so on and so forth. This is an infinite geometric sequence. And suppose we want to do this. Find the sum to infinity. That's what we want to do. Okay. So in other words, that's what we want to do. We want to find the sum to infinity of this one. So how are we going to do this one? Okay. First, we need to determine the common ratio. Common ratio, you divide second term by first term. And it's going to be a half, right? Positive. Absolute value of a half. I know we don't need absolute value on positive numbers, but I just want to make sure I understand this statement. Is going to be less than 1. Therefore, the sum exists. Good. Means we can do this. We can use the formula. Well, if something exists, we usually want to find it, right? So next we're going to find it. So how do I find the sum to infinity? Very simple. The sum to infinity of this sequence, if it was a series, means you add them up to infinity. You're going to get the first term. That's a1. Divide by 1 minus common ratio. Look how easy that is, folks. That's just remarkable, isn't it? You would think, look, wow, how do I find sum to infinity? That's going to be some complicated math, and it's not. Okay, so here we go. We got negative 48 divided by 1 minus a half is a half. I'm going to invert the half and multiply. Invert, you get 2 times 48. Negative 96. Check it out, folks. Isn't that great? If I add negative 48 plus negative 24 plus negative 12 plus negative 6, each time, notice, it's getting cut by half. Next time, negative 3. Next time, negative 3 halves. True. Next time, negative 3/4. And so on. All the way to infinity. All of this sum is going to be negative 96. And what's even more interesting, or I call it amazing, if you actually add these numbers, you will see the lion's share of this total is given by just adding the first few terms. Okay, so for example, if I add 48, 24, 12, 6, 3, 1.5, and 0.75 on my calculator, I got 95.25. Isn't that remarkable? The whole thing, the rest of this to infinity, infinitely many terms, it's only going to pick up 3/4. And that 3/4, again, we can actually go to like 316, 330 seconds, and the lion's share of that 3/4 is right here. So anyway, it's really phenomenal, folks, that this thing actually happens. But this only exists if the absolute value of common ratio is less than 1. Otherwise, disappointment. We can't do this. Okay? Now, let's do just one more and we'll be good to go for this section. We're going to do the same kind of work. Let's say, for example, this time I'm just going to write this in sigma notation. So here's the sum to infinity and infinite geometric series. There you go. If I put infinity on the upper limit of sigma, that means sum to infinity. And suppose I want to do 3/7 to the ith power. Okay, I want to do that one. So how is this going to work out? Well, because this is in the general form, by the way, check this out, folks. I have I1 to infinity of, let me put 1 times, okay, and actually let me change this. Don't like the looks of it. What I'm trying to do is this. Remember the nth term was a1r to the n minus 1. I'm trying to get it in this form. So for this, I'm just gonna do this. Let's say I can write this as 3/7 times 3/7 to I minus 1. Look, folks, isn't 3/7 to the first times 3/7 to I minus 1 exactly this? It is. So 3/7 to the first power is just 3/7. So that would be my first term. Therefore, A1 is 3/7. And what is the common ratio? The common ratio is the base, which so happens to be 3/7 also. So we have again uniquely identified this geometric series. Good for us. Now that we've done that, let's actually find the sum to infinity. Again, absolute value of 3/7 is less than 1. Therefore, S sub infinity means sum to infinity exists. And of course, we want to find it. So let's do this. The sum to infinity. Look at how easy the formula is. A sub 1. First term, 1 minus common ratio. That's it. First term is 3/7. 1 minus common ratio happens to be 3/7. And 1 minus 3/7, 1 being 7/7, right? Minus 3/7, that would be 4/7, wouldn't it? And you can cancel the 7s or invert and multiply 4/7. However you think of this, we all should get 3/4. And another remarkable result. If you add the terms of the series, and I'm going to write the first few terms of the series for you in just a moment. The sum to infinity is not even 1. It's going to be 3/4. Very darn close to it. Now, let's start to write out this series. I'm writing out the series. So when I is 1, first term, 3/7. Isn't that what we have here? That's another way, by the way, you can find the first term. Just write out the series. Let I be 2. That's 3/7 squared. Let I be 3. That's 3/7 cubed. Plus so on and so forth. All of these to infinity. Wow. 3/4. Isn't that cool? And there you have it. So, I don't know about you, but I'm impressed. So, hopefully this will help you with this section. And I think we're good. We've covered the key components of this section. So please review the video if you should, and hopefully again everything is clear, makes sense, and you're following what we're doing here. Okay, and as always, thank you for watching, everyone, and hopefully we'll have you in another video. Thank you.